You guys remember this problem? You remember this problem, right? So this problem, we have a mass here hanging down, so it just stretches the spring until there is a balance between the spring and this guy, and we are interested in determining the equilibrium condition. This rod has a fixed length L, and it was horizontal when the spring is unstretched. So this means that this distance is L minus X, right? Because this whole distance is L, then I stretch this guy X and I go down Y. Any question about this problem, the description? We are interested in determining the equilibrium condition, which means in Newtonian mechanics, do all the forces, summation of forces equal 0 and solve for your position, for your equilibrium state. In analytical mechanics, we do it a bit different. How do we do equilibrium in analytical mechanics? How do you do equilibrium?
Principle of virtual work.
Yeah. Principle of virtual work, that is great, that's right. So the summation of all the virtual work by the applied loads only, the only applied load here is the gravity, right? And the spring force. All the normal forces do not play anything. Is equal to 0. Alternatively, if it's a static equilibrium, how do you do it? Anybody remembers its principle of visual work? That's right. Equivalently, what's that?
Power.
If all your forces are conservative, what about the principle of minimum potential energy? Right? Get your potential energy and achieve its minimum. What's your potential energy? It's very easy to get. It's 1/2 kx squared for the spring and negative mgy for the gravity, right? So what is your dynamic problem or static problem? My static problem is to find the equilibrium. Now it's pure optimization problem. Minimize over x and y, v of x and y, correct? Is it an unconstrained optimization? Is x and y are free? Any one of them can take any values irrespective of the other?
No.
No, because they are constrained by this fixed length guy. So actually, this problem is subject to a constraint, which is y squared plus this distance squared, which is L minus x. This square plus that square equals L squared, which means it's minus L squared equals 0. Right? Correct? So, this is a mechanics problem, but now it's pure optimization problem. You can have this problem indeed in your 206 or in the prelim of the optimization or whatever, right? Has nothing to do with dynamics now, just this low. Okay? Let's solve it using the Lagrange multiplier rule. How do you do it? Well, if I'm minimizing v only, it's the gradient of v equals 0. But subject to a constraint, then you immediately do what? You form another function called Lagrangian. It's simply your objective plus lambda times the constraint. Right? So this is your v, it's 1/2 kx squared minus mgy plus lambda, which is unknown, times your constraint. Let's work our constraint a little bit. Y squared x squared negative 2lx. Okay? So this is lambda times all this. Y squared x squared minus 2lx. This is your Lagrangian, this green function. And then what you do? Deal with it, treat it as if your objective. Okay? It's partial L partial x equals 0, partial L partial y equals 0. The gradient of L now is 0, it's not the gradient of f. Partial L partial x is kx plus lambda negative 2L, right? Yes. Equal 0. Partial L partial y equals to, let's differentiate with respect to y, so here is negative mg plus 2 lambda y equals 0. These two black equations and how many unknowns? Two black equations and how many unknowns? 3. X, y, and lambda. What's the third equation?
Constraint.
The constraint. 3 equations and 3 unknowns, solve them. Yes, Anshul?
What about the x squared times lambda?
X squared what?
For d lambda dx, isn't there supposed to be minus 2l plus 2x times lambda? Or,
Here?
yeah,
This is the constraint, right?
right.
Let's get the constraints. Y squared, x squared minus 2lx. L squared minus L squared went away. So that's right. What? No?
For the derivative, isn't there should,
For the derivative, let's differentiate. So this kx. Oh, we have, you're right. We have 2x here. We have 2x. 2x minus 2l. You're right. Thank you. 3 equations, 3 unknowns. We're done. Any question? Yes, Mohammed.
For a function that has n variables, I think maximum we can have n minus 1 constraint.
Yeah, you can have any constraint, but then it's a strictly constraint problem. So there is no room for optimization. Your problem formulation dictated the solution upon you already. There is no room for optimization. If it's n minus 1, you're right. Then there will be room for optimization.
Then when we form this nabla and we take gradient, how many equations would that give us to equal to the number of
n plus m, right? How many equations from differentiation? The gradient, you always get n because you're differentiating with respect to the design values. You always get n, but you add in plus m constraints. N equations always get n from the gradient because the gradient n variables meaning n equations. Any questions so far? Then the fun part, go to the fun part, that is my favorite. The calculus operations. So, over there, so far, our optimum value was just a number. Or if it's x, y, z, w, at most, it's a bunch of numbers, so it lives in Rn, some n array, okay? So, and we were interested in minimizing f as a function of x. So if you are interested, if your problem, the optimal solution that you're expecting is a number or a bunch of numbers, the length, width, and mass of this guy, the span of the wing of the airplane, and aspect ratio, bunch of numbers, then you're pretty much doing this, okay? If you are expecting a function, the optimal shape of a function, then all this science is not useful for you. You need a calculus operations. So what's calculus operation? Now I'm not interested in minimizing f. Excuse me. You're not interested in minimizing f of x. Your f, let's call it j now, your objective. Let's give an example. So over here, I have my x, and I have my f. Give me x, I give you the corresponding f. Give me x, I give you the corresponding f. and so and so. And then this is your function behavior versus x. And I'm looking for the minimum. Over there, my x is a function of t. It's a function. It's not a number. It's not I give you a number, you give me f as a number. It's not even I give you an array of numbers, you give me f as a number. I give you a function, x of t, you give me a number, just a number. So this is x as a function of time. This is what I want. I don't want a bunch of numbers, an array. I'm looking for a function, the optimum shape of a function that say connects 0, 0 to 1, 1. I can connect 0, 0 to 1, 1 in infinitely many ways. Linear solution is one way. A sine-like solution is another way. Maybe exponential. Bunch of things. If you give me sine, put your sine and its derivative, get the integral because it's finite derivative, finite integral, right? It's definite integral. The result is a number. So if you give me sine, I give you a number. If you give me cosine, I give you a number. If you give me exponential, I give you a number. So this is now a hypothetical graph versus x, your function, something like here that we are used to. If you give me sine, I'll give you a value 1, for example. If you give me cosine, I'll give you a value 1 because they are the same. The derivative of sine is cosine, cosine is sine, and sine squared plus cosine squared is 1. So if you give me exponential for something, I'll give you here 0.35 exponential. If you give me linear, I'll give you 1.3. This is linear, right? This is a hypothetical graph. There's no such curve. And then you just do these points. I'm looking for the shape of the function that gives me the minimum of my j. You get what I'm saying? It's completely different view. It's quite a leap from minimization of in a single variable or n variables to minimization in infinite dimensional variables. I need infinite numbers because I need the shape of the function. I need its value at every point here in time, which is infinite number of things, right? I need the shape of a function. So whenever you're looking for a shape of a function, it is the calculus of variations. It's not finite dimensional optimization that we take into the process. Okay? Any question about that so far? Yes.
When we are minimizing, we are trying to find the minimum value or the minimum point. But when we are trying to find
two things. I'm trying to find the minimum value of my function f minimum and the value of x, the design variable that results in the minimum. The same here, I'm looking for the minimum j and x that results in the minimum j. But x here is not a number, it's a function. Okay? Yes, John?
So in this case, x would be an exponential as a function of t.
Yeah.
Okay.
Yes. There was a question back there? No?
Oh, so this is like trying to find a trajectory? Is that?
A trajectory is not the application. I'm coming here. I'll try to, hopefully it will give me maybe 5 minutes more today. I still have 5 minutes, so 10 minutes in total, because this has to be continuous. So, the branch of calculus operations actually started in before Christmas. There is one famous problem called Queen's Dido problem. What's that? Queen's Dido, in a nutshell, she was the founder of what we know now as Tunisia, North Africa. So in her journey, they wanted to settle in a place. So she asked the Berber king, please can you give us a piece of land, small piece of land, something like we can cover by an ox hide. Ox hide, we mean, or they mean, the leather of an animal, a bull. Hide is a bull, or ox is a bull. Hide is the leather of the animal. So they slaughter the animal, they have the leather of the animal, something like maybe this long, and you just need the land, some land to cover by this leather, okay? So the king said, okay, yeah, go on, take whatever land, small, that piece. She tricked them because what she did is that she cut this leather, this sheet of leather, she cut it in very fine strips. Now she has the strips, okay? And she's solving the following problem. What is the shape of this enclosing perimeter or circumference that maximizes the enclosed area? Subject to a fixed length of perimeter constraint, right? Maximization of the enclosed area subject to a fixed perimeter length. This was Queen's Diagonal problem. Let's get a bit more serious. This is the very origin of the science. Of course, she didn't do it mathematically like we're doing it, but the guys who did it mathematically, like we're doing it, was Johann Bernoulli. This is the first serious construction of calculus of ratio. In his paper, 1697, he solved something called the Brachistochrone problem. What's the Brachistochrone problem? It's the following problem. It's a problem in dynamics, by the way. So he has the following. Well, I have a certain height, h, and I have a ball here that is starting from rest, and it will slide down some smooth curve. And I want this ball to come down under the action of gravity in minimum time. What is the shape of the curve along which this ball will just roll over to come down in a minimum time? So I'm looking for the shape of the function. If this is x and this is y, then I'm looking for y of x. What is y of x that minimizes the total time of the excursion? Okay?
Is x known?
X final, you mean?
Yes.
Yes, because it's. So in other words, I need to connect these 2 points. How can I connect these 2 points? What's the shape of the connecting shape that results in minimum time? Let's formulate this problem because we know how to formulate it. Let's do it. It's very easy.